Hey everybody, welcome back to chemistry. And so now what I'm going to do is I'm going to talk about ions. And so there are a bunch of formulas for ions that you need to know, and those formulas will include a symbol for an atom or symbols for many atoms. And then in addition to that, you'll need to know what the charge of the ion is. And so there are basically two kinds of ions you're going to have to know about. They're the so-called monatomic ions, and then there are the polyatomic ions. So I have here a slide that kind of explains what these things are. So if I can increase the slide. So let me point out that a monatomic ion is an ion that is made of one atom only. And a good example of that is the sodium ion. And so let's compare that to a polyatomic ion. A polyatomic ion is an ion that has two or more atoms bonded together. An example of this is the sulfate ion, which formula is SO4 2-. Can I reduce the slide? So let's go ahead and look at an example of this monatomic ion, which is the sodium ion here, versus the sulfate ion, which is a polyatomic ion. So just to point out, a neutral sodium atom, you can look up its atomic number. It is 11. Therefore, the neutral sodium atom will have 11 protons and 11 electrons. But here, the sodium ion is different than a neutral sodium atom. It is missing an electron, so it only has 10 electrons. And so what that means is the sodium ion has an extra positive charge. And so what we're going to do is we're going to put a plus here to remind ourselves of that. And so to indicate that we're really referring to the sodium ion instead of, say, the sodium neutral atom, is we write Na+. So as soon as I see that positive charge here, I remember that this is an ion. In particular, if it's a positive charge, then it's going to be a cation. Okay, so now let's consider here the sulfate ion. So one thing you can see is that the sulfate ion is a lot larger, and the reason is the sulfate ion is made of 5 atoms bound together. So we have a central sulfur atom, and then we have 4 oxygens attached or bond to the sulfur atom. And so here, this thing here, the sulfate ion, it has 48 protons, but we have learned in order to stabilize this ion, it needs to grab 2 extra electrons from someplace else. So you might wonder where the 2 extra electrons go. And what we have found is they really don't go to any particular atom. They tend to kind of wander around the whole molecule here. And so to indicate that we have these 2 extra electrons, I put the whole thing here in brackets like this, and I write 2-. Now let's write a formula for sulfate. It's going to be SO4, single sulfur atom, 4 oxygens, and then the whole thing has a 2- charge. Okay, so let's move on to the next slide. So if I can increase the slide. Okay. So one of the things you're going to have to do is you're going to have to know the formulas and the charges for these monatomic ions. And so let me point out something that might be a little bit helpful. So you might recall where the dividing line between the metals and the nonmetals are. And so the metals will be to the left of that red staircase line, while the nonmetals are to the right of that red staircase line. And so one of the things I'm hoping you'll notice is that everything to the left of that staircase line, when you have a neutral metal and it becomes an ion, it's always going to lose electrons. And so you can see sometimes here in this row, the elements lose 1 electron and become a single positive charge. Sometimes they lose 2 electrons and get a 2+. And then occasionally you have like aluminum here that will happen to lose 3 electrons and become 3+. So again, when metals become ions, they will always lose electrons. And when you have a positively charged ion, it's called a cation. Now let's look at the nonmetals here. So here we're looking at the nonmetals. And so what I'm hoping you can see is that the nonmetals, when they become ions, tend to gain electrons. They have more electrons than protons in the ion, and so they're called anions. And so you can sort of see that every nonmetal here that becomes an ion here in this next to last column gets a single charge, and then one over to the left, it gets 2 extra electrons, so it gets a double negative charge. And then here, nitrogen gets 3 additional electrons, and it will get a 3 negative charge. Now, you might ask, why is it that the elements like in the first column tend to want to lose 1 electron only and not lose 2 electrons or 4 electrons? And why maybe the elements here in this column here, which includes oxygen, why do they always gain 2 electrons and not, say, 3 electrons or 4 electrons or lose an electron? The reason why atoms tend to lose or gain electrons is so that they can achieve a noble gas configuration which is stable. So I'll explain that in just a second, but I want to show you a trick which will help you figure out what the charge is for these various monatomic ions. If you find that the element forming the ion is only going to be part of this first column here, which is a part of the alkali metals, it will have a 1+ charge. So for example, lithium here, when it becomes charged, will be 1+. It'll never be anything else. Potassium here, when it becomes charged, it'll be 1+ also and never be anything else. And so here with the alkaline earths, it'll be 2+. And then you'll have to remember that you just kind of skip over the transition metals and you go over here to aluminum here. And I'm hoping you can remember aluminum, when it becomes an ion, is always 3+ and never anything else. What we're going to do is we're going to talk about the noble gases in just a second, but let's go to the next to last column here. So this next to last column is the halogens. When a halogen becomes an ion, it must become 1- charge. The next column over, which includes oxygen, sulfur, selenium, tellurium, polonium here, here these elements, when they become ions, have a 2- charge. And then also nitrogen and phosphorus, when they become ions, they have a 3- charge. And so one of the questions you might ask is, why didn't I say indicate that arsenic is 3- and here antimony is 3- or bismuth is 3-. And the reason is these elements tend not to be found in ionic compounds. And so another thing I want you to understand is you can think of the noble gases as having a 0 charge. And the reason is this: noble gases, whether it be helium or neon or argon or krypton or xenon or radon, and then I'm not sure what this one is, but anyway, these noble gases tend to not want to lose electrons and become positively charged, nor do they tend to want to gain electrons and become negatively charged. They're happy as they are, so they will never find them charged. And we'll talk a little bit more about why that is the case a little bit later on. Okay, so you might recall that I told you that what a neutral atom will often do is it's going to either lose a certain number of electrons or gain a certain number of electrons to get a noble gas configuration. So let me try to explain that really quickly here. So let's just look at lithium here. And so let me remind you here that a neutral lithium atom, so this is the neutral atom, this is not the ion, this is the neutral lithium atom, has 3 electrons in it. And so let me remind you of its configuration. It's 1s2, 2s1. Now, lithium will lose 1 electron. It'll be down to 2 electrons here. And when it loses an electron, it will be positively charged. And so what's this ion's configuration? It is 1s2, because the 2s1 electron is gone in the lithium ion. And so here in the lithium ion, it's only 1s2. It really has helium's configuration. And so helium, you might recall, is a noble gas here. And so what you can see, what lithium did is it lost exactly 1 electron to get helium's noble gas configuration. It didn't lose 2 electrons, it didn't lose 3, that would be too much. You want lithium to achieve the nearest noble gas configuration, and that will really stabilize the ion. Let's look at magnesium 2+. And so magnesium, the neutral atom, has 12 electrons. And so its configuration is 1s2, 2s2, 2p6, 3s2. Now, what is the magnesium 2+ ion? So the magnesium 2+ ion is going to have 10 electrons. It's missing 2 electrons. And its configuration is 1s2, 2s2, 2p6. And that's it. It has lost those 3s2 electrons. And so if you notice here this configuration, this is neon's electron configuration. It only has 10 electrons. And so when magnesium loses 2 electrons, goes from 12 to 10, it picks up the noble gas configuration of neon, so it stabilizes it. And so that's why magnesium loses exactly 2 electrons and nothing else. Okay, let's do one more. Oxygen here. So oxygen, the neutral oxygen atom has 8 electrons. Again, this is the neutral atom. And so it's 1s2, 2s2, 2p4. But oxygen can gain 2 electrons and get a 2- charge. It becomes oxide. It has 10 electrons, and its configuration is 1s2, 2s2, 2p6. So oxide here has neon's 10 electrons, and so it has neon's electron configuration, which stabilizes it. So I think what you can see is all of these ions here have the charges they do because that was the necessary number of electrons to either gain or lose to get a noble gas configuration. Okay, so there's some additional monatomic ions whose charges you need to memorize, and so let me point those out. Scandium, when it becomes an ion, will have a 3+ charge. Zinc, when it becomes an ion, will have a 2+ charge. Silver, when it becomes ion, has a single positive charge. And then cadmium, when it becomes ion, will have a 2+ charge. So one of the things I was trying to point out is with these ions I've gone over so far, they can only have one possible charge state. So for example here, what I pointed out before is that the alkali metals here, they can only be 1+. They can never be 2+, 3+, 1-. And so if they can only have one charge state, then these ions are all called monovalent. So valent has a lot of different meanings, but one definition for valence is the number of charge states it can have. And so all these ions can only have one charge state, and so these are all monovalent ions. But here's the thing. Not all ions are that way. And so one of the things you're going to have to memorize here is that copper is not a monovalent ion. This is actually a divalent ion in the sense that in a compound, copper can either be 1+ or 2+. Okay? Same thing with iron. Iron can either be 2+ or 3+. And so this one is another one you're going to have to memorize. And so there are a bunch of other transition metals that are divalent like this. So you have to know that when an ion can have 2 or more possible charge states, they are called polyvalent ions. So one thing that you need to do is, again, memorize all the ions and their charges that I have up here, but also you're going to have to keep in mind that all of these other spaces that we did not give formulas and charges for, these are also all metals. We do not expect you to know the charges for these metals here, but just please remember that you should assume that all these other ones are polyvalent, meaning that the metal can have 2 or more different charge states. Okay, so now we move on to polyatomic ions. I'm going to talk about the ones of these that you have to memorize. And so here is a listing of the formulas and charges of the polyatomic ions that you have to memorize for this class. So let me first remind you why these are not monatomic ions, but they are polyatomic ions. And so let's look at this example here of carbonate. And so if you were to look with a super powerful microscope as to what carbonate looks like, you would see there's a carbon atom here, and there's a single bond to an oxygen atom like this, and then there's a double bond to this oxygen atom, and then there's a double bond here to another oxygen atom. It's unstable as is, and so this whole thing, to stabilize it, needs 2 extra electrons, so we indicate that by putting a 2- like that. And so the reason why carbonate is a polyatomic ion is this is an ion, as you can see, that is made of 4 atoms with 2 extra electrons. And so, for example, I've already drawn a picture of sulfate. Let me draw the bond structure of sulfate if you're curious. Here is sulfur in the middle, single bond to one oxygen, single bond to another oxygen, and then you have a double bond to this oxygen and a double bond to this oxygen. And then this whole thing has a 2- charge. And there's one more thing I need to point out. Some tables will have acetate with this formula here, which is C2H3O2 with a single minus charge. But another way you might see it is CH3CO minus. So if you happen to see it like that, that is also an acetate ion. They're exactly the same thing. And if you look carefully, you see that both formulas have 2 carbons, 3 hydrogens, 2 oxygens, and a negative charge. It's just that the organic chemists like to write it out like this oftentimes. So you have a need to memorize sheet for this class, which is posted on the course details website. And so that lists out the names for the polyatomic ions and their formulas and charges that you need to know. Okay, so I can give you one helpful rule that might help you figure out what the formulas and charges are for polyatomic ions. So here's that one helpful rule. If you have 2 names for polyatomic ions that are the same except that one starts with the word hydrogen, so for example, let's say you're considering 2 polyatomic ions. One is called carbonate and one is called hydrogen carbonate, and you're trying to figure out the formulas for them. This may help you. They have a similar formula except that the name with hydrogen has an H stuck onto the formula and 1 less negative charge. So in the case of these 2, you'll just have to flat out memorize that carbonate is CO3 and then it has a 2- charge. But let's say on the test you have to give me the formula for hydrogen carbonate. How would you do that? Well, my hope is you can remember that carbonate here is, again, CO3 2-. Hydrogen carbonate is going to be the CO3 like before in carbonate. You stick on an H to it, but then you take away one of the negative charges. So it's not HCO3 2-, it's now HCO3-. And so you might wonder why that is the case. So the reason why that's the case is, think of hydrogen carbonate as a carbonate here with a hydrogen plus stuck onto it. And so if you add the plus to the 2- here in carbonate, what you'll get is a sum of a single negative. And so that's why it's that. Okay, well, thank you for listening. We'll see you next time.